Well, we shall start back, we shall resume then. Okay. So, when we look into the learning outcomes, actually they are described in four levels as you can see. The first is the conceptual commitment must be clearly distinguished from economic dispatch. The second is the mathematical, the objective function and the constraint must be interpreted in terms of real power systems operations. The third is the procedural, that is the priority list. Heuristic must be applied correctly. The fourth is the algorithm. The dynamic programming recursion must be used to construct and recover an optimal schedule here. So the important point is that the final outcome is not simply the ability to memorize a recurrence equation. A dynamic programming solution is meaningful only when the state definition, feasible state screening, production cost, transition cost, and backtracking logic are all understood. A numerical table without the correct state interpretation can easily produce a plausible looking but physically infeasible schedule. So, the complete chain should therefore be visible, identify the feasible unit combinations, calculate the economic dispatch inside each feasible combination, add startup cost when moving between combinations, retain the cheapest path to every state, and finally backtrack from the least cost terminal state. So, well, introducing the unit commitment problem. Here, this marks a conceptual transition from continuous generation allocation to commitment scheduling. Understand, you are not running the entire generation set fleet of, if you have five generators, you are not running all the five generators for 8 hours, 10 hours, or 12 hours. What are we doing here is we are scheduling. We are committing to certain units, like first 3 hours, these set of units will run. For the next 2 hours, combination of units will run. This is what we call it as it's not a continuous uh, transition from a continuous generation allocation to a commitment scheduling. Okay, so the central change is subtle but it is very important. A power system does not merely decides the numerical output of machine, it decides which machine should be synchronized, which should remain on standby, and which should be shut down completely. So the reason for making this distinction is the daily variation of load. The generating fleet is normally sized to survive the highest expected demand and required reserves, but that same full fleet is unnecessary during the low load periods. A schedule is therefore required that can follow the daily load pattern without paying the operating cost of unnecessary machines. Once time enters the problem, the decision can no longer be made by looking at each hour in isolation. So a machine that appears unnecessary in the current hour may be worth keeping online because it will be required shortly. So conservatively, a machine that is cheap to operate must still be undesirable if demand is too low to accommodate its minimum output. Okay, so these are the few things we actually have to look into. Fine. Unit commitment is therefore uh, uh, an optimization of operating status over time, not simply an.
Slide ಮೂವ್ ಆಗ್ತಿಲ್ಲ.
Hello.
Slide ಮೂವ್ ಆಗಿಲ್ಲ.
No, no, I'm still in the same slide. Don't worry. I can move. I'll go back and I'll move. I'm trying to give a generalized picture of how we are working on this. Okay. Uh, Fine. If you don't want so much of introduction, I can move. No problem. Yeah. So from economic dispatch to unit commitment. So economic dispatch method uses for contains an implicit assumption. The candidate generators are already running. Once the assumption is removed, the optimization requires an additional layer here. So the output variable P determines the continuous loading of generator, while the binary variable U determines whether the generator is available to produce at all. So the realistic daily load curve may have a low overnight valley, a morning rise, afternoon plateau, and an evening peak. It is economically unreasonable to keep every generator online through the entire horizon. So merely because of some of them will be needed at evening peak. Units that are online incur fuel right and no load costs that may also force the load to be spread over more machines than necessary. So unit commitment question is therefore formulated over the entire planning horizon. For each hour, a subset of units is selected. That subset must possess sufficient capacity to meet the forecast demand and reserve requirements. Within selected subset, generation is dispatched economically. The total objective includes operating cost of the selected units and the cost of starting units that were previously off. The resulting problem combines binary scheduling with continuous dispatch. Further explanation, the binary status also changes the geometry of the optimization problem. Economic dispatch searches inside a continuous region defined by generator limits and power balance. Unit commitment first chooses among many disconnected continuous regions, one region for each feasible on-off combination. After a state is selected, economic dispatch searches inside that state's continuous region. The full UC problem is therefore a collection of continuous dispatch problems connected by discrete transitions over time. So, what is a useful way to visualize the problem is to imagine the daily load curve moving across a fixed generation fleet. The fleet is available physically, right? But its members need not to be synchronized. Unit commitment selects the economical and operational appropriate subset before the dispatch calculations even begins because the selected subset can change with time. The schedule must be judged as a sequence rather than a collection of isolated Harley answers. So now the question is, what is unit commitment problem? The one line definition, as you can read from the uh, slide there, or else contains three ideas that should be separated. First, the schedule extends over a time horizon, commonly day ahead in hourly intervals. Second, the objective is economic. The schedule should minimize total operating cost. Third, the schedule must remain feasible under both system level and unit level restrictions. So, the mixed integer nature comes from the coexistence of binary commitment status and continuous power output. The binary variable changes the mathematical character of the problem dramatically here. A continuous variable can take any value within a range, but a binary variable forces a discrete choice there, right? With many units and many hours, the number of possible on off patterns grows extremely rapidly. So, this problem is also time coupled. If a unit is turned on now, minimum uptime may prevent it from being turned off in the next hour. If it is turned off now, the minimum downtime may prevent it from restarting immediately. Okay, so startup cost may be, startup cost may depend on how long the unit has remained off. Therefore, the feasibility and cost of a decision at a R, if you consider it to be any T, depends on operating history before RT. This is fundamental reason the R's cannot simply be optimized independently. So further explanation to add on to this is, the or else combinatorial growth should be interpreted as a warning against naive enumerations, not as a claim that every theoretical combination is physically possible. See, demand, reserve, and unit. These limits eliminate many states. Minimum up and down time eliminates many transitions, right? Nevertheless, a remaining search can still be enormous. Central task of every unit commitment solution method is therefore to exploit structure so that the solver does not spend equal effort to every imaginable schedule there. Therefore, you have an equation here you can see, right? This commitment creates a discrete schedule over time. A very useful way to visualize the problem is to imagine the daily load curve moving across a fixed generation generating fleet. The fleet is available physically, but its members need not all be synchronized. So, unit commitment selects economical and operationally appropriate subsets before the dispatch calculation begins there. Because the selected subset can change with the time. The schedule must be judged as a sequence rather than as a collection of isolated Harley answers. Next question. Why not just run every available unit? Anybody can answer this question. Why not just run every available unit? No need of unit commitment, no need of any complex mathematical thing. Why can't we do that? Sanjita, Uday, wait. Sanjita, these people are not present, man. Rashmi, Salman, Mamta.
Yes, sir.
Yeah. Why can't we run all available units? Okay, Uday. Fast. Uday?
ಸರ್ ಎಸ್ ಸರ್.
Yeah. Can you answer?
ಅದನ್ನು ಈಸಿಯಾಗಿ ಸ್ಟೋರ್ ಮಾಡೋಕ್ಕಾಗಲ್ಲ ಸರ್, ಲಾರ್ಜ್ ಕ್ವಾಂಟಿಟಿ ಆಫ್ ಗ್ರಿಡ್ಸ್.
No. If we try to manage, like, if you have 200 megawatt load, you have 5 generators, why can't we put 40, 40, 40 and run all the 5? Store ಬರದೇ ಇಲ್ವಲ್ಲ. Okay, losses ಸೇರಿಸ್ಕೊ 51, 51, 51 ಮಾಡಿ. You can have 205 or 52, 52 ಮಾಡಿದ್ರೆ 210 megawatt of power can be generated. Right?
Yes, sir.
Yeah.
But power generation must perfectly matching between demand real time.
Yeah, demand is 200. Losses may come up to 10 megawatt. ಅಷ್ಟೊಂದು ಬರಲ್ಲ 5 megawatt. So 1111 schedule ಮಾಡಿದ್ರೆ 51, 51, 51 you get 205 megawatt of load. Perfectly matched.
Yes, sir.
Now tell me why every generator can't be run.
Maximum capacity ಇದ್ದಾಗ demand is low ಇರುತ್ತೆ ಸರ್. Run at all times.
Okay, the answer is running every
Generation limits.
Yeah.
ಜನರೇಟರ್ ಮಿನಿಮಮ್ ಲಿಮಿಟ್ಸ್ ಇರ್ಬೋದಲ್ಲ ಸರ್ ಅದ್ರ ಜನರೇಟರ್?
ಅಲ್ಲ 50 ಮೆಗಾವಾಟ್ ಇದೆ ಅಂತಾನೆ ಅನ್ಕೊಳ್ಳೋಣ, ಲಿಮಿಟಲ್ಲಿ ರೇಂಜಲ್ಲೇ ಇದೆ ಅಂತಾನೆ ಅನ್ಕೊಳ್ಳೋಣ. ದ ಆನ್ಸರ್ ಈಸ್ ವೆರಿ ಸಿಂಪಲ್, ಇಟ್ ಈಸ್ ಅನ್ಎಕಾನಮಿಕಲ್. ಎಲ್ಲ ಜನರೇಟರ್ನು ಸ್ಟಾರ್ಟ್ ಮಾಡಬೇಕು, ರೈಟ್? ಕೆಲವು 50 ಮೆಗಾವ್ಯಾಟ್ ಅಂಡರ್ ಪಾರ್ ರನ್ ಆಗ್ತಿದೆ, ಅಲ್ಲಿ ಆಪ್ಟಿಮಲ್ ಆಗಿ ಅದು ಯುಟಿಲೈಸೇಷನ್ ಅಲ್ವೇ ಅಲ್ಲ. ಎಲ್ಲದರಲ್ಲೂ ಡೀಸೆಲ್ ಇಸ್ ಬರ್ನಿಂಗ್ ಔಟ್ ಆರ್ ಥರ್ಮಲ್ ಫ್ಯೂಯಲ್ ಇಸ್ ಬರ್ನಿಂಗ್ ಔಟ್, right? So that is the reason it is usually uneconomical. Synchronizing a thermal generator is not a zero cost state. Fuel is required to maintain the steam conditions, auxiliary system operates, rotating equipments remain active, isn't it? And no load components of the production cost is incurred even before the unit contributes substantially useful power. So part loading, we call it as part loading, can also be economically unattractive. ಅಂದರೆ ಪಾರ್ಟ್ ಲೋಡಿಂಗ್ ಅಂದರೆ 50-50-50 ಅಂತ ಏನು ಶೇರ್ ಮಾಡೋದ್ವಲ್ಲ, ದಟ್ಸ್ ವಾಟ್ ಯು ಕ್ಯಾನ್ ಸಿ ಹಿಯರ್. ಸ್ಪ್ರೆಡಿಂಗ್ ಅ ಮಾಡರೇಟ್ ಲೋಡ್ ಅಕ್ರಾಸ್ ಮೆನಿ ಯೂನಿಟ್ ಫೋರ್ಸಸ್, ಈಚ್ ಒನ್ ಬಿಲೋ ಇಟ್ಸ್ ಮೋಸ್ಟ್ ಎಫಿಷಿಯಂಟ್ ಆಪರೇಟಿಂಗ್ ಪಾಯಿಂಟ್. See, if moderate system demand is divided among too many units, each unit may operate close to its lower output region. The resulting operating point may be less efficient than the concentrating generation on a smaller number of suitable units. At the same time, committing too few units creates opposite risk. The system may be unable to meet demand, they may lack reserve, or may be unable to respond to contingencies. This creates the central economic tension of unit commitment. More committed capacity improves security, flexibility, but raises the cost of keeping machine available. Less committed capacity reduces immediate operating cost but can create infeasibly and excessive risk. Yeah, less committed means if you're having 200 and you're having capacity to run for this 200, load is 200 and you're running two generators or three generators, like 60, 60 or 65, 60 something, if there is a sudden inrush of load, you have to start one more generator there, because all of them are already operating at their peak maximum. So even having the less is also that will reduce your immediate operating cost surely, but it is infeasibility and excessive risk involved. So the optimization problem search for the lowest cost compromise, like you need to have the some generators in standby also, and also you should run with a proper demand which has been created now, and also you must have a low operating cost. You should also supply complete load. This is where the word optimal comes into picture, the entire class of this. There is also important security interpretation. Keeping more units online generally increases flexibility and reserve, but it can create larger minimum generation problems. If many thermal units are committed, their combined P minimum value may exceed low net load. This issue becomes especially relevant in systems with high solar output, where net demand seen by the thermal unit can fall sharply while some units remains constrained by minimum operating levels. So, what is a useful way to visualize the problem is to imagine the day load curve moving across a fixed generating fleet. The fleet is available physically, right? Uh, Unit commitment selects that economical and operationally appropriate subset. Therefore, the dispatch calculation begins. Because the selected subset can change with time, the schedule must be judged as a sequence rather than a collection of isolated Harley answer. So the combination, the combinatorial nature of unit commitment. The combinatorial difficulty can be understood directly from the number of possible unit states. With n states, every unit has two possible statutes, right? Either on or off. Excluding the meaningless all off combination when demand exists, a single hour may contain 2 to the power of n minus 1. Right here you have minus 1 possible commitment combinations, and the difficulty becomes much larger when the schedule contains several hours. If the Harley states were treated as independent, the number of complete schedule would grow as the number of Harley combination raised to the number of time periods. So, for even a small number of units, this increases an enormous search space with realistic unit counts. Exhaustive enumeration is not merely inconvenient, it is computationally meaningless. So, time coupled constraints reduces the number of feasible schedules but do not remove the fundamental difficulty. In fact, they make a new enumeration more complicated because the feasibility of state depends on the proceeding state. This is why structured methods are necessary. A priority list reduces the search through a simple ranking assumptions. Dynamic programming exploits the principle that the best way to reach a state can be stored and reused. Later methods such as Lagrange relaxation, MILP are designed to handle such larger practical systems. See, the state count also explains why time coupling is more damaging than a simple increase in number of generators. See, adding one more unit doubles the binary possibility within the stage, right? If you include one generator, again two possibilities came in. Either that extra unit should be on or off. But adding one more hour multiplies the number of complete schedules by the number of hourly states. So the origin therefore has profound effect on computational complexity. A useful way to visualize, uh, let's move ahead. If you want me to give the example of what we are already having here, okay, you can see there are three units. So you will be having 7 combinations. So out of t is equal to 24 hours, 7 to the power of 24, you will get this answer. Already impossible by hand, right? When it comes to 10 units, you will be having these many combinations, and just look at this number. Can you even read it? Impossible for any computer to. 40, typical utility. This is the combination you will be having approximately, that is also astronomically large number. Full enumeration is meaningless. Okay, so where unit commitment sits in the operational timeline, such a beautiful heading this is. Then where exactly we are talking about the impossibilities, we are talking about the problem, we are talking about the contingencies, hurdles, hiccups of handling unit commitment all through. So where exactly this unit commitment sits, where exactly it will help us is the question remaining with us yet, right? So unit commitment occupies a specific position in the hierarchy of power system operations. Long-term planning asks what capacity should be built years in advance. That is a capacity expansion problem. Unit commitment assumes the fleet already exists and decides which of those units should be available over the coming operational horizon. After commitment comes economic dispatch. The committed units are given output set points that satisfy the present load economically. At a still faster time scale, automatic generation, control and regulation continuously adjust the output of selected online units to maintain the frequency and interchange schedules. The hierarchy is therefore based on time scale and decision type. Long-term planning changes the asset base. Unit commitment changes the set of online assets. Economic dispatch changes the megawatt allocation among those assets. AGC makes second by second corrections around the scheduled dispatch. Understanding this hierarchy prevents a common confusion. Economic dispatch and unit commitments are not competing solutions to the same questions. They solve different layers of the same operational problems. See, the boundaries between these layers are not perfectly rigid in real control rooms. Day ahead UC is repeatedly updated as a forecast change. Intraday commitment may revise earlier decisions, and uh, real time dispatch may operate over rolling intervals. Nevertheless, the hierarchy remain useful because because it identifies the dominant decision at each time scale. Cost constraints in UC. Again, the most relevant. What all involved? See, when we look into Uday, I will change the slide. I want to give a bit of introduction here because this is what gives you understanding about the next slides. See, the yeah, I don't want you to think that I'm not moving the slide. The unit commitment objective cannot be understood by looking only at the fuel cost curve. The realistic commitment schedule is influenced by several cost components and by restrictions that arises from both the power system and generating unit themselves. At system level, every hour must satisfy the power balance and maintain sufficient reserve. At the unit level, each committed generator has minimum and maximum output limits and may have restrictions on how quickly it can start, stop, or change output. Minimum up and down time creates the strongest connection between successive hours in classical formulation. So the objective therefore measures more than the cost of producing electrical energy. It measures the cost of deciding to make generating capability available. The distinction becomes particularly important when a load peak is brief. Starting a unit for 1 hour may appear economical when only fuel cost is considered, but the startup cost and subsequent minimum operating time may make the decision expensive over the complete horizon. The constraint in this section should not be treated as an independent add-ons. They interact. A startup decision changes the commitment status. A commitment status activates generation limits and no load cost. Minimum up and down time restricts later transitions. Reserve may require additional units to remain online. So the difficulty of unit commitments comes from this interaction between economics and security and time. So if you look into the objective functions of unit commitment, this is where the real unit commitment starts. So the objective function combines time, operating status, and transition cost. The other summation runs across the scheduling horizons. See, the inner summations runs across the scheduling horizons. Sorry, uh, the the outer summations runs across the scheduling horizons here, not the inner. I was looking into this inner summations. The outer, this runs across the scheduling horizons, while the inner summations runs across all generating units. This is the cost function from the previous example. You know that, right? Similarly, these all run with the uh, generating units. Here, the first term, this term you have in the inner summations. This first term, this represents the production cost when the unit is committed. A particular unit is committed. The binary state thus acts as on and off switch in the mathematical expression. So the startup term detects the transition from off to on. Obviously, if you have a startup thing, if the unit was off in the previous hour, then you will be having this unit will become 1. What you have inside the bracket, this will become 1, because this becomes 0, so this becomes 1. Okay. If the unit is on in the current hour, multiplication by this ui minus t keeps the term active here. So the product therefore 1 only for an on off to on transition. In all other transitions, this becomes 0. This is basically 1. Okay. In all other transitions, this becomes 0. So this becomes 0. So you will be left out with only this parameter. Okay. This compact expression is most important because it reveals why the problem is time coupled. See, the cost at RT depends partly on this thing. Okay. In a dispatch problem, the cost is usually determined by the present output. In unit commitment, the cost of being in a state also depends on the state from which the unit is arrived. See, the objective shown is intentionally compact here. More complete formulation may include shutdown cost uh, and fixed maintenance cost, reserve procurement cost, emission costs, fuel constraints, and penalty terms. The compact form is still sufficient to expose two fundamental cost types: the cost of remaining in a state and cost of moving into a state. It might be on state or off state, anything. Okay. So the constraint in this formula should not be treated as an independent add-on. They interact. Okay. The three cost component, very important now. We were talking about the cost component, right? So the three cost component should be interpreted separately. The fuel or running cost is the familiar input output curve of the generating function, sorry, for generating unit. In the simplest statement, it is represented by a quadratic function here, right? Almost same to your cost function from the uh, see exactly the quadratic term from section 1 to 4, applicable only while unit u of uit is equal to 1. Uit is equal to 1 means it is in on state. Okay. Well, this term changes continuously with the output, because whatever the output you are getting, this is completely dependent on that, so this term will keeps on changing. So then you have the no load cost. This is associated with keeping the unit synchronized and available, right? It is simplified quadratic model. The constant component contributes to the cost when the unit is operating. It explains why statement why the statement the unit is producing very little power does not imply the unit is almost free to keep online. Online means it is why the unit is on just in case. So startup cost is different again. The transition cost rather than a steady state cost. It is paid when unit changes from off to on. Do remember this startup cost comes into picture only from off to on. Okay, and may include warm up fuel, wear means belt drive, anything it might be wear and tear, what we call it as auxiliary consumptions and operating uh, effort. Because startup cost may be substantial, a schedule must compare the savings obtained by shutting a unit down uh, and because startup by shutting an unit down against the cost of bringing it back later. So this comparison is one of the reason unit commitment must consider future hours. See, the distinction between running and transition cost also explains uh, a common scheduling trade-off. Just to give an example, suppose a unit can save $100 by being shut down for an hour, but restarting it later costs $400. So the local saving does not justify the transition. Conversely, a sufficiently long low load interval may justify shutdown because the accumulated no load and fuel saving eventually exceeds the later startup cost. Startup cost is what I was talking about. We'll continue that. Please have a look here. We have two types of cost now in the startup cost. One is hot start, another one is cold start. Okay, so I'm going to explain each one of them. Uh, Please be attentive, it's very important. A thermal unit here, does not forget its previous operating condition immediately after shutdown. If it has been off for only a short period, thermal unit does not forget in the sense if the generator body, radiator, whatever the all the things involved to start a generator is operated for a quite a good hour number of hours, they all heated up. Now you shut them off, they doesn't get cool at, it doesn't changes the transition immediately. It's not a binary, it gradually cools down. If you are going to start it after 5 7 minutes, it's still hot. That's what it means. So, if it has been off only for a short period, significant thermal energy remains in the equipment. So, restarting the unit requires less additional energy. I totally agree. And preparation than restarting is completely. The restarting the unit requires less additional energy than starting a coal plant. This leads to a distinction between hot start and cold start. See, the exponential expression here, it provides a smooth model of this transition at zero off time. Here you have startup cost if switched on almost immediately after shutdown. Okay. See, C cold is startup cost if the boiler is fully cooled. Then you have T of number of hours the unit has already been off. Alpha I cooling time constant of unit cools. Large alpha I cools slowly. Smaller alpha I cools instantaneously. So at zero off time, the exponential term is 1 and the startup cost is close to the hot start value. As off time increases, this T off increases, the exponential decay towards zero, causing the startup cost to approach the cold start ceiling there, right? Because your generator is moving towards the cold or getting cold uh, more rigorously if the T off is more. So the cooling time constant controls the rate of change I mean, a larger value represents lower cooling and therefore a longer period during which the unit remains relatively warm. The model is important conceptually because startup cost may be depend not only on whether the transition occurs but also on duration of preceding off state. More advanced unit commitment models therefore track unit history in greater details. See, the exponential startup model is convenient, continuous approximation. Some practical systems instead uses discrete hot, warm, and cold categories based on the threshold of downtime. But we are not using warm here in this particular equation. The underlying physical idea is the same there. Thermal state deteriorates with time off, right? So the next startup cannot be valued independently of shutdown history. So the constraint. Let's have a worked calculation for the startup cost. So problem is the unit has a hot C hot from this equation. Startup cost hot start is 150, cold start is 500, and cooling constant is alpha is equal to 4 hours. Find the startup cost if it has been off for 6 hours. It has already been off for 6 hours. Cooling time constant alpha is 4 hours. It has gone beyond it, right? So now we have to compute first. See, physical meaning. This worked example will illustrate the physical meaning of startup model for you. The unit has, as I explained, hard start of $150 and cold start of $500. The difference between these two. Okay, what is the difference between these two? It is $350. Where you want this, you can see here. C cold minus C hot. You can substitute directly 350 of the previous example of the next slide example here, right? Well, so the difference of $350 is additional cost that gradually appears as unit will unit cools. After 6 hours of off, the normalized off time is 6 by 4 because 4 hours is the cooling time. So 6 by 4 T off by alpha will give you 1.5. What is this 1.5? This is a normalized off time. The exponential e raised to minus 1.5 is approximately 0.2331. The exponential. You have the exponential here. Can you see this? So this value is 0.2231, right? So the fraction of the cold start transition that has effectively occurred is 1 minus this. This will give you the answer of how much? 0.8? No. 7769. So the answer for this bracket, okay, is 0.7769. Well, multiplying this fraction by hot to cold difference gives us you have to multiply with this thing with 350. This will gives you an answer of, for this entire expression we have dealt it step by step. This will give you an answer of, what is the product of that? 272. How much? Okay. So now you have got this entire thing. Now add it with hot start base. Hot start, how much was the hot start? 150. So this was 150. If you add these two, you are going to get the starting cost as 421, I guess, or 422, you can say, dollars. So am I right? Yes. See, this is very much closer to cold start ceiling, that is 500, since 6 hours exceeds one cooling constant, right? The result is physically sensible. 6 hours exceeds the cooling time constant, so the unit has moved substantially towards the cold condition, but the cost has not mathematically exceeded the cold start ceiling, and means this has not went beyond 500, right? uh, this example also shows why simple fixed startup cost assumption is an approximation. The same off to on transition may have different economic consequences depending upon the unit's prior downtime. Like if the downtime uh, was 2 hours, 1 hour, 3 hour, you would have got a different answer here, right? This ratio would have changed. This ratio would have changed this. That would have changed this. That of course will change this product, and then the entire sequence will be changed. So this is what will you can actually summarize how exactly the cooling time matters in our unit commitment. So when we this was one example. When we look into a larger picture, when we take the when we take this to power balance constraints, like system level constraints. So when we talk about the we can divide this topic into two. That is, one is the spinning reserves and another one is the power balance. So we'll discuss with the power balance first. So power balance constraints requires the total output of committed units to equal the forecast demands. So for each hour in the simplified lossless formulations, the binary commitment variable here ensures that off unit contributes no generation to the balance, right? And if you look at the spinning reserves, is a different from generated power. A system can meet the present demand exactly and still be insecure. So the committed fleet must retain additional immediate usable capability so that a sudden outage or demand increases can be accommodated. So the reserve means if you can keep a generator on, but it's not delivering power; it's just on. You can start your scooter, especially not the bikes. When you start your scooter, it will be on, but it will not move until unless you further accelerate. Right? That is somewhat called a spinning reserve. I mean, you can correlate. That is not called as spinning reserve. You can correlate. So the reserve inequality therefore compares the total maximum capacity of committed units with the present demand plus requires safety margins. This explains why commitment is based on capacity as well as the energy cost. A unit may be committed primarily to provide a reserve even if its scheduled energy output is small. So in real systems, the definition of reserve can also include response time, ramp capability, and contingency requirements. The simplified equation used here captures the essential principle. Enough online capacity must exist to absorb a credible disturbance without immediate load sheddings. So, reserve should be distinguished from energy. A generator producing 200 megawatt with maximum capability of 300 megawatt may contribute 100 megawatt upward headroom, right? Subject to ramp and response time limits. A generator may already at maximum output contributes energy, but little immediate upward reserve. Thus, the commitment decision determines not only how much energy can be produced, but how much flexibility remains as well. So, the constraint in this section should not be treated as, that I'll come back to this when we take up the numericals. Here, when we talk about unit level constraints, see, we'll take about each unit rather than the entire power system, or in a larger picture. Someone wants to join, talk, anything? What happened?
No, sir. Nothing.
Something popped out, right? Anyways, yeah. So, generation limit defines the feasible output range of a committed unit. So once a unit is on, it normally cannot be dispatched below a technical minimum or above its maximum rating. So these limits interact with the binary commitment variable. If unit is off, its output must be zero. If unit is on, the output lies within the operating range. Minimum uptime prevents rapid shutdown after startup. The restriction reflects thermal and mechanical realities and avoids economical unrealistic cycling. So minimum downtime performs the opposite role. Uh, After shutdown, a unit may require a minimum period before another startup is permitted. These restrictions are not merely an extra inequalities. They create memory, kind of to know whether proposed on-off decision is feasible in the present hour. The algorithm may need to know how long the unit has been continuously on or off. In dynamic programming, this history must be presented either directly in the state or indirectly through feasible transition screen. In full mathematical UC model, unit commitment we can call it as UC from here on. So in full mathematical UC model, the binary status is often used to enforce limits in one expression, uh, such as UIT of P minimum. Uh, I mean, we use this for P minimum, P maximum in our previous cases. You can add UI of T. When unit commitment is zero, that is output is forced to zero, right? When U is 1, the ordinary operating range becomes active. This formulation makes the connection between binary commitment and continuous dispatch explicitly. Okay. So, minimum up, down, and downtime. This is what has been illustrated through this slide here. Uh, the illustrated timeline, as you can notice there, should read. I mean, you should be careful because minimum time constraints are often misunderstood as a simple labels rather than restrictions on further decisions. The unit is switched on at R3, H3, marked in yellow here. Yeah, as you can see here, right, with this line. And minimum uptime for 3 hours. Therefore, the commitment beginning at hour 3 creates an obligation to remain through hours of 3, 4, and 5. So the shutdown at hour 6 is first permitted off transition after satisfying the minimum on duration. Once unit is shut down, a new obligation begins with a minimal downtime of 2 hours. The unit must remain off during 6 and 7 hours. It cannot be restarted during this interval simply because a short demand increase occurs there. So only for 8 hours onwards, the required off duration elapsed. This example shows you why hourly optimization is inadequate. A decision made at hour 3 constrains the feasible decision at several future hours. The resulting sequence is therefore a path of problem which is exactly the structure dynamic programming is designed to exploit. See, the timeline also reveals why minimum time constraints are path constraints rather than simple state constraints here. Two schedule can reach the same on-off state at R6 but have a different feasibility in R7 if the unit has been on for different durations. A rigorous state definition may therefore need to encode duration information, not merely the current on and off vector, right? So, what are the other practical constraints we have? Very similarly, we had in load dispatch also, if you remember. I mean, I think in the last session. See, practical unit commitment contains many additional restrictions beyond the basic textbook formulation. Ramp rate limits the constrain the change in generator output between successive periods. A unit may have enough nameplate capacity to meet the future load, but if it cannot ramp from its current output to the required output quickly enough, the schedule is not operationally feasible, right? That's the constraint, therefore. Must run constraint. This arises when a unit is needed for reasons other than pure energy economics. Local voltage support, reliability obligations, contractual arrangements, or technology specific requirements may force a generator to remain online. So fuel and emission limits can create constraints over the entire horizon rather than a single hour. So then you have uh, crew and plant resources constraints are also examples of operational coupling. If multiple units share startup equipments or operating personnel, starting them simultaneously may be impossible. These practical constraints illustrate why industrial unit commitment models are much richer than the compact classroom objectives. See, the basic mathematical structure remains the same, but the feasible set becomes more complicated for us. Uh, ramp limits strongly with commitment. Starting a unit may not immediately provide its full maximum capacity, and shutting it down may require ramp down trajectory. So, modern unit commitment formulations can therefore model startup and shutdown power trajectories rather than treating the transition as instantaneous. Okay, beautiful thing. Solution methods. See, the solution method section moves from a simple intuition towards increasingly powerful optimization techniques. The simplest approach is to impose a fixed priority order. This dramatically reduces the search but sacrifices optimality because same ranking is used regardless of operating history. Dynamic programming introduces memory across stages and can provide an optimal solution within the retained state space. Its main limitation is the growth of the state space as the number of unit increases. Then you have Lagrange's relaxation, and I think if you remember, I talked about MILP, mixed integer linear programming are introduced as the next steps in the course because they addresses the scaling problem differently. If we talk about the Lagrange relaxation, it decomposes the difficult coupling constraints using multipliers, while MILP represents the binary and continuous decision explicitly and relies on modern branch and bound and cutting plane solvers. The important conceptual progression is therefore not that one method simply replaces another. Each method changes the way the large combinatorial problem is structured. The priority method is useful pedagogically because it separates the idea of ranking from more difficult idea of scheduling. Ranking answers which units are generally attractive to operate. Scheduling must additionally answer when they should be started and stopped. The difference between these two questions is exactly where time coupled optimization begins. So we can have an overview of the solution approaches here. See, the solution approaches can be compared by asking how each one deals with the enormous search space. We have priority list. It reduces the search by assuming that unit can be placed in a fixed economic order. This makes the method extremely fast, but it can miss the schedule that are cheaper over time. Okay. Then we got the dynamic programming. It retains the multiple feasible states and compares the cost of reaching each state from the previous hour. It can therefore recognize the It can recognize that a state with a slightly higher current cost may create a cheaper future path. Its optimality is exact only within the state and transition retained by formulation. Then we got Lagrange relaxation. With a Lagrange relaxation is a valuable for large system because it relaxes coupling constraints and permits decomposition into smaller subproblems. Although coordination is then required. So MILP is dominant modern formulation because binary commitment variables, linearized costs, and operational constraints can be handled by powerful commercial solvers. This comparison should be understood as a comparison of computational strategy. The physical UC problem remains the same. The methods differ in how they search or decomposes the feasible schedules. See, one thing you can understand, no single solution method is universally best. Small classroom problems benefit from dynamic programming because recursion exposes the logical optimal substructure. Large industrial systems benefit from the MILP because modern solvers uh, exploits sparsity, branching, cutting phases, and resolves techniques. The choice of method depends on the scale, required optimality, model detail, and available computational time. The priority list method is useful pedagogically. Now we shall look into priority list method concept. Okay, we are taking one by one. So if we look into the priority list method, is the simplest structure heuristic for unit commitment. Each generator is assigned an average full load production cost, average, obtained by dividing its full load operating cost by its maximum output. Units are then sorted from the lowest average cost to the highest. For a given hour, units are committed in that order until their until their cumulative maximum capacity is sufficient to cover demand and any required reserve. The actual generation is then determined by economical dispatch. So the priority ranking itself does not prescribe that every committed unit operates at maximum output. So the strength of the method of this priority method is its simplicity. The ranking is calculated once and reused. However, the same feature is also its weakness. A fixed ranking cannot recognize that startup cost, minimum uptime, current operating state, or future demand may make a different combination preferable. The method is therefore best viewed as a heuristic screening or teaching method rather than a complete solution to time coupled unit commitment. See, average full load cost uh, is only proxy for a true economic attractiveness. A unit with a low average full load cost may have high startup cost or a high minimum cost output. Another unit with a higher average cost may be preferable during the short interval because it is already online. This is why the priority list is useful as a ranking heuristic but cannot replace multiple period optimization. We'll have an example for a priority list method. In this worked example, the first task is not to dispatch the unit. The first task is to rank them. For every unit, the full load cost is divided by corresponding maximum output. Fine. You can see 4 units are available. Forecast demand for the hour is 500 megawatt. Unit priority list method using decide the unit that commits. Okay. So now you have minimum. A should have minimum 60, maximum 300. Full load cost, that is 300 megawatt cost, is 1200. Similarly, here it is for B is this and 900. So when you have this average, you will be having an average cost here. Depending upon the average cost, priority is given. First priority to meet 300 is A. It will run at 300. Second priority is B. Fine. In any case, B is shut down. Next priority comes to 3. 3 alone cannot, because 300 plus 150 will give you 450. Then comes the fourth. Okay. So the forecast demand of 500 megawatts starting from the highest priority unit, maximum capacities are accumulated. The first unit alone is insufficient if its maximum output is below the required demand, right? The second unit is then added and the cumulative capacity is checked again. Unit continues to add until the capacity requirement is covered, right? The result is commitment decision, not at the final megawatt schedule. So one committed set is identified. Economic dispatch determines the actual outputs. This distinction is important because a unit can be committed for capacity and reserve purposes without necessary operating near maximum outputs. When applying this example, the capacity accumulation should be viewed as a feasibility screen rather than an economic proof. Once the chosen unit have sufficient maximum capacity, the exact outputs still need to be found by economic dispatch. If reserve is included, the cumulative capacity targets must be demand plus reserve, not demand alone. Okay. Strengths and limitations of priority list. See, the priority list is fast because it reduces a complicated scheduling problem to a single sorting operation and repeated capacity accumulation. So, for a small system with a similar units and modest time coupling, this can provide a useful first estimate. Its limitations, however, are fundamental. A ranking based only on the average full load cost cannot represent the startup cost. A unit that is cheap when running may be expensive to start. The rankings also ignores the minimum up and down time. So an hour by hour application may propose sorry, transitions that are physically impossible, right? Most importantly, the method has no longer genuine memory of the future. It can decide which unit looks attractive in the current hour, but it cannot fully compare the cost of sorry, yeah, uh, it cannot look attractive in the current hour, but it cannot, but it cannot fully compare the cost of staying in one state now against the future cost of moving to another state later. Dynamic programming introduces precisely this missing element. The best cost of reaching a state carries the history forward in a compact form. So, the failure is fixed ranking becomes most obvious around peak and valleys. A ranking can identify which unit is generally cheaper to operate, but it cannot decide whether the unit should be started early, kept online through a valley, or shut down and restarted later. So those decisions depends on the duration of the future load pattern. So we shall move with the dynamic programming now. After priority list, see, we had this priority list done here. The first one, we had a worked example. We understood how the priority list works. We understood the limitation. We understood how its merits and demerits and everything. Now we shall move with the dynamic programming, how it works. Okay. So when we have to talk about the dynamic programming, uh, is introduced because unit commitment has natural sequential structure. The scheduling origin can be divided into stages, usually hours. Every stage, the system occupies one commitment state, and the decision is the transition to the state in the next stage, right? The method does not attempt to store every possible complete history separately. Instead, it stores the best known cost of reaching each state. Once cheapest path to a state is known, any more expensive path reaching the same state can be discarded, providing the state contains the information needed to determine future feasibility and cost. This is essential computational advantage. A multi-hour schedule is represented through a sequence of state transitions, while repeated subproblems are solved once and reused. So, in the coming slide, we will going to talk about the Bellman's principle, which we discussed in the yesterday's class, if you remember. and translate states and costs directly into the unit commitment problem. So the DP formulation is best understood as a shortest path problem on a layered graph. Each hour forms a layer, each feasible commitment state is a node in that layer, and each permitted transition is a connection between layers. Production cost belongs to the destination nodes for current hour, while startup cost belongs to the transition. The cumulative DP value is the least cost of reaching the node. So we will look into the Bellman's principle of optimality. A recap in the sense we discussed it during the ELD. So Bellman's principle optimality provides the theoretical foundation for dynamic programming. Once the system has reached a particular state, the remaining decisions must be optimal with respect to that state. The complete history that produces the state does not need to be re-optimized if the state itself contains all information relevant to the future. So in unit commitment, the stage is naturally represented by time, hour 1, hour 2 and so on for the sequence of decisions. The state is feasible combination of units that are on together with an additional history information required by the constraints. So the recursion uh, then compares possible predecessor states, you know, to determine the best way to reach a state at hour t. The algorithm doesn't enumerate all complete schedules from hour 1 again. It takes the already known best cost of each feasible predecessor. Uh, so adds the transition cost, current production cost, and retains the minimum. This reuse of optimal substructure is the heart of dynamic programming. See, Bellman's principle works only when the state has been defined sufficiently. If the future cost depends on piece of history that is not represented in the state, the two histories reaching the same apparent state may not actually be equivalent. This is why realistic DP formulation may augment the state with time since startup or time since shutdown information. So the DP formulation is the best understood as a shortest path problem on a layered graph. Each hour forms a layer, each feasible commitment state is a node in that layer, and each permitted transition is a connection between layers. Production cost belongs to the destination node for the current hour, while startup cost belongs to the transition. So the cumulative DP value is the least cost of reaching at that node. So let us see the formulating unit commitment as a DP problem, stages and stages. Okay. Um, the precise DP formulation requires meaning of each terms to be fixed. A stage is 1 hour in scheduling horizon. A state is one feasible commitment combination at that hour. The decision is the choice of which feasible state to occupy, given the state occupied in the previous hour. So the stage cost contains two parts. First, there is a production cost of meeting the current load with the units committed in the selected state. This cost is found by economic dispatch. Okay. Second, there may be a startup cost associated with the units that changes from off in the predecessor state to on in the target states. So the cumulative cost, F cost, here you can see F cost of t comma k is the least total cost of arriving at k at rt. The definition is crucial here. The algorithm does not store every route that reaches state k. It stores only the cheapest valid route. The identity of the best predecessor is stored as well so that the complete optimal schedule can later be reconstructed. See, the phrase feasible state must include more than capacity here. A state must have enough P maximum but violate reserve minimum generation must run conditions or history dependent restrictions. Just for the classroom example, feasibility screening is intentionally simple so that the DP recursion can be easily seen clearly. Real implementations uses richer state and transition tests. So here, the dynamic programming recursive cost equation. See, uh, the recursive equation can be read from right to left as a comparison of all possible ways to enter the current state. So we shall come from here. As you can see, f cos t minus 1 comma L. This is best known cumulative cost of a predecessor state L. To move from L to the current state K, newly started units generate a startup cost. Here you have that S cost from L to K. Once state K is reached, the current R load is supplied at the production cost of P cost T comma K. So what I want to tell you is this is production cost at current production cost. Okay. So this is the startup cost from L to K. So F cost is the cumulative cost of a predecessor state L. Well, so the sum of these three quantities gives the total cost of reaching state K through predecessor L. Okay. The minimization over L here, you can see minimum over L selects the cheapest feasible predecessor. That minimum becomes F cost T of K. So the equation therefore separates three economic ideas. The past represented by already accumulated cost, the transition represented by the startup cost, the present operating cost. Three ideas represent the production cost. This separation makes the logic of the numerical DP table transparent. Each entry is not an isolated hourly cost, it is the best cumulative cost of a complete path ending up in the specified state. So the minimization over a predecessor L is local in form but global in consequence. Because F cost, the last one, cumulative cost, already contains the best history before our T. Choosing the cheapest predecessor automatically accounts for all earlier decisions. This is the mathematical mechanism by which DP avoids complete remuneration of the past. This is algorithm. So the forward algorithm begins by listing feasible states for each hour. So feasibility must be established before cost comparison. A combination that cannot meet the demand and reserve requirement should not enter the DP table. Next, the production cost of every retained state is calculated using economic dispatch. This is where the mathematics of the earlier session is reused. Equal incremental cost is applied to the committed units with generator limits enforced. At R1, the known initial condition acts as a predecessor. Startup costs are added for the units that are initially off and become on. At each later R, every target state is compared against its feasible predecessors. The minimum cumulative cost and the identity of the predecessor that produces it are stored. After the final R is processed, the state with the lowest cumulative cost is selected. The predecessor pointers are then followed backward. The forward pass computes the cost, the backward pass recovers the actual schedule. So the forward algorithm can be implemented as a table, a layered graph, or a set of arrays. Regardless of implementation, the stored data are the simple in principle. Current state identifier production cost, best cumulative cost, and best producers. The table is therefore not merely a bookkeeping here, it is the data structure that embodies the recursion as well. You can see the flowchart. So the flowchart is algorithmic representation of the recurrence. The process uh, starts with a known initial status for the current hour, the feasible commitment uh, sorry the feasible commitment states are identified. Each state is economically dispatched to determine its production cost. The current state is then connected to the feasible state, right? So from the previous hour, so for each connection the algorithm calculates the transition cost and adds it to the stored producer cost and current production cost. So the least cost producer is retained, the time index is then advanced, the same sequence repeats until the final hour. Only when the entire origin has been processed in the optimal terminal state identified. So the schedule is then reconstructed by backtracking. The important feature of this flowchart is the separation between the forward computation and the backward reconstruction. The algorithm does not need to know the complete optimal schedule here, okay, during early hours. It is only needs to preserve enough information to recover uh, uh, that schedule after the final cost compromises. See, the loop terminates only after the final origin stages has been processed. Backtracking step is initially separated from the forward loop because choosing the cheapest state at an intermediate hour would be greedy and could destroy the future optimality. So DP dynamic programming delays the final path decision until the entire horizon has been considered. That's one thing you can always keep in mind. So truncation strategies that reducing that state space. See, dynamic programming is powerful, but it is not immune to the growth of the state space. If every possible combination of units is retained at every hour, the number of states can still become impractically large. Okay, capacity feasibility is the first and safest screening rule. A combination whose minimum and maximum aggregate outputs cannot cover the required operating range is impossible and should be discarded immediately. This removes states without risking the loss of optimum because they are physically infeasible. So, priority order neighborhoods. This provides an additional heuristic reduction by concentrating on combinations near the economically attractive ranking. Minimum up and downtime can also eliminate impossible transitions before cost comparison. So, the important distinction between the safe pruning and heuristic truncation. Eliminating infeasible state preserves exactness. Eliminating a feasible state for computational convenience may improve speed but can theoretically remove the true optimum. This distinction should always be stated clearly when evaluating a truncated DP result. So, when we talk about the truncation strategies, must be reported transparently. If the state set is reduced by strict physical feasibility, the optimum over the original feasible model is preserved. If economically unlikely but feasible states are removed, the state must become optimal only over the retained subset. This distinction is important in research reporting and algorithm comparisons. So this is beautiful. Dynamic programming versus exhaustive search. See, the numerical comparison here they demonstrates why structured search is valuable. with 3 units. Okay, there are 7 non-empty commitment combinations in 1 hour. If every combination across 3 hours were compared independently, that would be 7 cubed. So 343 possibilities, state sequences. Most of these sequences are irrelevant because they cannot meet the specified load. Feasibility filtering reduces the candidate states to those combinations capable of serving each hour. The example then requires evaluation of only the retained state set and feasible transition. So the stated reduction of approximately 97% illustrates the principle rather than a universal ratio. The exact saving depends on the load profile and system characteristics. Nevertheless, the computational logic is general. Do not spend optimization effort on combination that can be rejected by simple engineering feasibility tests. So dynamic programming gains further efficiency because best cost of state is stored and reused rather than recalculating complete histories repeatedly. The numerical reduction is especially meaningful because the savings are achieved before sophisticated optimization begins. Basic engineering knowledge but about the capacity and load can eliminate most impossible schedules there. Good optimization model therefore combine mathematical algorithms with a simple physical screening rather than treating every candidate as equally worthy of computation. So let's understand the startup cost in DP transition. See, we're talking about the startup cost in the transition property. This is one of the most important ideas in the entire DP formulation. The cost here cannot be assigned to the target state alone because the same target state may be reached from different predecessors. For example, you know, consider the target state in which unit 1 and 2 are on. Okay, uh, if both units were off previously, both startup costs are incurred. If unit 1 is already on and unit 2 was off, only unit 2 incurs the startup cost. If both were already on, there is no startup cost. Therefore DP table must compare the state pairs, not merely state costs. The target states has production costs associated with serving the current load, but the path into the state determines the transition cost. This is why the recurrence includes startup cost L to K, if you remember in the equation, rather than simple S cost K. The distinction also explains why a state with the lowest production cost in the current hour may not have the lowest cumulative cost. A more expensive operating state may be cheaper to reach because it avoids costly startup. The same target state can consequently have several incoming edges with different costs. This is the graph interpretation of the startup cost. A node there, it represents the current commitment combinations, but the edges represents the how what had to be changed to reach it. Backtracking to recover the optimal schedule. At the end of the forward pass, the DP table contains the minimum cumulative cost of reaching every final state. The smallest of these identifies the optimal terminal state. However, the terminal state alone does not tell us the complete Harley schedule. During the forward recursion, the algorithm therefore stores the predecessor responsible over every minimum, starting from the cheapest state at the final hour, and stored pointer identifies the best state in the predecessing hour. So repeating the process traces the optimal path back to R1. So backtracking is therefore not a second optimization. The optimization has already been performed in the forward recursion. Backtracking simply reconstruct the sequence that produce the stored minimum. This logic is similar to shortest path algorithms. A cost label indicates the best known route to a node, while predecessor record allows the route itself to be recovered after the destination is selected. So backtracking also provides a useful diagnostic tool. If the final schedule looks surprising, tracing the predecessor chain reveals exactly where the algorithm made a trade-off. This is often more informative than looking only at the final total cost because the chain exposes the specific startup year and production cost comparisons that determine schedule. So, uh, we shall end up here for today's discussion. I have few more things to, very few things to discuss. I'll take it up in the